All right, everybody, let's get started. Welcome to the final colloquium of the semester until next year. And especially welcome to Megan Schufreider, who is from the California Academy of Sciences. And for those who don't know it, that's an institute at the in the Golden Gate Park in San Francisco. And amazingly, it houses an aquarium, a natural history museum, what else? A planetarium. You're good. A 4-story rainforest, all under the same roof. So it's an amazing place to visit. I highly recommend it. And the building itself serves as a facility for scientific research and also as a public resource with thousands, actually millions of specimens and artifacts. Megan is Assistant Director of Student Education, and she's responsible for the development, delivery, and evaluation of pre-K-12 educational programs and materials associated with field trips, homeschool events, summer camps, virtual programs, family nights, and also classrooms. Megan has a bachelor's degree in Ecology, Behavior, and Evolution, and also in Japanese from UCLA, and she has an MA in Museum Studies from San Francisco State University. Previously, she was a middle and high school classroom teacher, as well as an educator in various informal settings. And so we're very happy to have Megan here today, and she's going to be presenting Understanding the Next Generation Science Standards. How can informal education partners play a role? Welcome, Megan.
Thank you. Thank you very much for inviting me to speak today. I'm really glad you've all shown up to learn a little bit about the Next Generation Science Standards, because it's something that myself and my institution and a lot of other Bay Area institutions, formal and informal, are excited about. I have come today with a presentation that hopefully will get done in an hour. I want to give credit to some of my colleagues in teacher professional development. Sarah Soule and Catherine Danielson put a lot of these slides together for some teacher professional development we did this summer. And my colleague Ben Lavender, also, he's actually an alum of the Graduate School of Education here. And he runs our Teacher Institute on Science and Sustainability. So throughout this presentation, I've kind of scattered a bunch of resources that they might have pulled together physically on the screen, and so I give them props for making the slides for me. And then I've morphed in some discussion about how informal science education institutions in the Bay Area can play a role with this, because it's something we're excited to grapple with, and we've already started. I heard that there'd be a lot of students who might be pre-service math or science educators, and so I thought that this might be pretty relevant for you right now to get started. If at any time you have questions, I'm not averse to answering them, so you can, if it's something that you need clarifying right away, feel free to shoot a hand up, but we will have time, obviously, for questions and answers later. So hopefully today what we'll do, we'll talk a little bit about why we need these new science standards. Hopefully by the end of the day you'll understand the conceptual shifts. How are they different from our current state standards? How many of you pretty much know, you've been to the website, you've actually had to design something, you know what the current state standards look like? Anybody? No? Okay, a little bit, okay. Who knows what NGSS looks like? Ooh, good, okay, I have a lot of newbies, I love it. Great, so you'll definitely learn something. I'll tell you how we got here, and a little bit about how it might be implemented, and talk about how informal science institutions can play a role. So first, just to get, come on, join us. Get you in the mindset. I want you to think back to when you were maybe a kid in your science education, and think of how that worked. Right now you might be a little biased because you might be studying science a little more. But think about these statements, true or false. Scientific ideas are absolute and unchanging. The process of science is purely analytic and does not involve creativity. Science is complete. It's a solitary pursuit. And it's boring. Can you think of any time in your science education career where you might have thought that or perceived that in class? And a few others, we might not do them all, but we work closely with UCMP here at Berkeley on a few projects, and so we have to throw some of theirs in here. Their wonderful Understanding Science website has some other misconceptions about science. Because scientific ideas are tentative and subject to change, you can't trust them. Or perhaps that the best ideas are those that just are the most popular. If everybody thinks it's right. Or if you get a whole bunch of correct hypotheses, you're the best scientist. You're going to win awards having the most hypotheses that basically are supported by evidence that you can find, or that science is a collection of facts. All of these bullet points that I've shown you are not how we think science is, but if you think to how you were educated, it's possible that some of this might have snuck in there. It's just a relic of how we've been taught. So, quick pop quiz. How does students learn science best? Kind of a leading question, just a little bit. Hopefully everyone kind of agrees that the best way to learn science is by doing hands-on science. Nothing wrong with reading about science or preparing for a test, but in order to get really good at it, you usually have to do it. Right now, our science education system is a lot about facts. Facts, facts, facts. This is what science is. Learn how to do this. And the problem with this is that students don't get a chance to actually do science. They don't get a chance to actually manipulate things, solve things, ask questions, and so they don't get that skill base that they're going to need later. They also don't understand how science as a process is. They might think it just is something that one smart person does in a solitary hall. They discover something. They don't understand the collaborative process of science, how you have to work together, how you have to work off some of the others' ideas. You have to share that idea. You have to get critiqued. That we're building off others' experience. And they don't always relate to science or feel that it's important. This is some classic drawings. I'm sure you've heard of these or maybe even done these before, but when we were doing a project with the Diang, which is an art museum in San Francisco, it was about art and science and how the skills for art and science actually do overlap, even though people don't often think that they do. And we had the students, before they took the program, as a pre-test, draw what they thought a scientist looked like, and as a post-test, draw what they thought a scientist looked like. And you'll note with the pre-tests, these are just two examples, but students often are seeing the stereotypical white male in a lab coat in indoor environment, doing something lab work related or with explosions. And by the end of the experience, the students were able to put themselves in that role. They were able to put minorities in that role. They were able to be outside and doing different types of science. So hopefully we can change our science education so that we're not always in this mold. It's fine to do science in this mold. We're all cool with lab coats, but it's just not the only science. So why isn't there more hands-on science? One big reason of the last decade is testing. It's great that we want to assess our students. We need to know what they're learning. We need to know, is this effective? But because we've done it only through pencil and paper tests, we've had to teach to this test. And the way that our educators have been trained to teach to this test is through standards. This is just a very, I know you can't really read this, a screenshot of some of the current standards for science education in California. And all of the statements start with students know. So students know that decomposers are part of an ecosystem. Students know that they need to be able to analyze how climate, human activity, and all the systems of the earth are related. Students know that biodiversity is the sum total of all the different species in the area. It's about facts. So the current science standards, if you looked at them, most of them are written students know, students know, students know. And it's either physical science, life science, or earth science. That's how they group them in elementary grades at least. When you get up to secondary school, things are a little more regimented into discipline. And then there's a portion that's currently called the investigation and experimentation standards. And these are the ones that give teachers the flexibility to teach students how to do science. So those are the things like students know how to ask questions, they know how to pick the right tool for something, they know how to design an investigation, they know how to pick their variables, that kind of thing. This is what currently the science standards in California look like. And it's not that we don't want kids to know facts about science, it's just because we've focused so much on that content, we've lost on what science education really could be. So we decided we really need to change this up. One reason is that in the past 15 years, we've had these standards since 1998 in California. Science has changed, right? So if all of your science education is about facts, and you wait a decade, those facts are going to change a little bit. You need to put new stuff in the mix. We also have learned more through research. So we've done a lot of research into learning, how students learn, how people learn, how can we do science education best. So over that past a dozen years, a lot of national organizations have released those studies, and then trying to figure out how can we put that evidence into our work. And also, even though we've been testing, if you compare us to international students who are not at the top of the pack, and we wanted a system that is internationally benchmarked. It's going to set our students prepared, not just for careers here, but if they were to work anywhere, if they were to be compared around the world, they'd be on top. So, with that in mind, we had to make a better K-12 science education system. It was decided that we should shift things a little bit around. The first one, we'd want to reflect the interconnected nature of science. So right now, you might learn physical science, you might learn life science, you might learn earth science. You learn, here's some facts, here's some facts, here's some facts. And there's not a lot of connections in between them. But science in the real world ends up having, even though you do end up specializing a lot of the time, you do need knowledge of all of them, and you do need to know the trends between them. So that's one thing that for our new standards, our new education, we wanted to put in the system. And then rather than having what they call a mile wide, inch deep, where you know all types of content, but you only know a little bit of it. You know a lot of content, but you just barely scratch the surface. Let's shift that so that you could have a deeper understanding of content, but on less of it, so you could do it a little better, and you know how to actually apply that to the real world. So not just here's some knowledge, but let's use that. Why do we even care? You know, is that it's going to help us solve something? Is it help us going to improve society? Are we just going to know more about the natural world? Why? Also, based on some of that research on education, understanding where students are developmentally and how they should learn at different stages. Are they learning the right content in that grade? How can we shift it about to make sense more, and how can we build on it? Right now there is, if you looked at the standards now, you can tell, they learn geology in 2nd grade, 4th grade, 6th grade. You can tell that they're building from past years, but sometimes it jumps a little too much, and sometimes compared to what they've researched now, you're not learning what you could at that age, or it's just too much for you. So making a better progression was one of the key points for the new standards, and preparing students for the real world. So college and career readiness is big. One other big conceptual shift that has to do also for college and career readiness is including engineering in the standards, because currently engineering is not seen barely at all in the California science standards. So that was a big conceptual shift to put that in. So very briefly, we're going to talk about where they came from. So back a few years ago, the National Resource Council, which basically is part of the body that provides advice to our government on scientific matters, created a group of people that involved science education researchers, Nobel laureate scientists, policy experts, educators at the time, to create what it was called a framework for K-12 science education. And what this is, it's actually pretty easy to read. It lays out content that anyone should be expected to know if they were to graduate from high school and go to college or get a career. This is the science that you should know. So they work to try to make the content, reduce it to the big concepts, and figure out how to make progressions, or at least start to make the progressions for what students should know. And then they basically put it to the states, or a group of lead states, there happen to be 26 of them, to draft the standards in more detailed form in order to get it approved for the nation. So the whole goal of this was to say this is what our nation of kids needs. It's not something that's going to come from the government down, but here's the research. They also did the 12 to 15 years of research. This is based on research. This is what we think they need to know. Now it's up to other experts to pull it together, create a draft of the standards for us to see, can we as a nation approve this? So it went to these states. These happen to be the lead states. You'll see that California was one of them. The director of Teacher and Youth Education, Meg Burke, at the Academy happened to be on the committee, and there were others from other institutions around the Bay Area there as well, and they met in Sacramento to help draft these standards. They went through lots of experts actually trying to create them, and it went through many, many rounds of open public sessions until they created what they thought would work. Then it was, the same version was kind of sent out to all the states to adopt or change according to how they saw fit, and that's kind of where we're at now. Okay, so the standards have been, they were drafted, they were finalized, and now they're going out to states to adopt, and I think we're going to talk about timelines in a little bit, but California did adopt them. In order to actually get the standards document, which they did finally print, and if anyone wants to see the printed one, it's all online too, but you can definitely check it out. In order to get this print version, we needed someone who was unbiased to get a group together to say, okay, the framework looks great. Everyone kind of likes the framework, but we need to put it into something that a teacher can use, even though it's not curriculum. And the bipartisan independent body that was chosen is called Achieve, and they were formed in the mid-1990s, I think 1996, by actually state governors and business leaders who wanted a workforce that was ready. So they wanted students to finish high school and really be ready scientifically. That's who founded Achieve. They were chosen to kind of lead this together with a new group of experts. So I just kind of want to point out, because this is this other body that's heading this up, it's not really the federal government that's creating the standards. So even though the idea is that we want this to be a nationwide, every state accepts it, everyone then, all the kids are doing the same thing, because right now all the state standards are different. California could be totally different than Utah, could be totally different than Illinois. Let's make it so that it's at a place where everyone feels comfortable with it, so that I can kind of get kind of that bottom-up support. Okay, so it's not, federal government isn't funding it. They haven't, nor will they in the future. Instead, Achieve and the National Resource Council, in order to do this, got private funding, which is great. Private money is good. And also the support of some other big players, so the National Science Teacher Association, which supports and advocates for science teachers, Association for the Advancement of Sciences. Basically, they're some of the kind of the biggest advocates to make sure that this got done. And what they came up with, which we're all kind of really happy about. Sorry, do you have a clarifying question?
Are there any federal funds that are conditioned on accepting the NGSS? Because that's the other way of defining it as government involvement.
Not that I know of. That whereas you would be eligible to receive federal funds upon. Not that I know of.
Okay.
Yeah.
So what is it that's like convincing schools to adopt these?
Well, so if the state adopts it, if at the state level adopts it, then it's for all public schools, then must use them eventually. Timeline, we'll talk about timeline a little bit. So it really is just public schools. So private schools, just like now, can do what they want to do. Charter schools, even though they're kind of pseudo-public, sometimes based on their charter they can do, it's like an alternative. There's different classifications, so they don't have to do it exactly. They don't have to exactly follow these. So it's public schools. So if a state adopts it and decides to implement it, eventually there will be assessments made to test the students, and all public schools will then have to, if they want their students to succeed on those tests, conform to those standards.
Do you expect all the states to adopt these?
Great question.
Especially like states in the South that don't accept a warning inoculation.
Yeah, great question. We expect, or those that have been on the committees that I've spoken with, expect most states to. They think the holdouts might be Texas and Alaska. But 48 is still pretty good. All states recently, at least to my knowledge, anyone can correct me if I'm wrong, but the Common Core, which is the English language arts, and the math equivalent of national standards. Everyone, let's keep all the kids on the same page for English language arts and math. I'm pretty sure all states accepted those. This is kind of the equivalent, but for science. Yeah, great question. But hopefully, maybe there's enough peer pressure, right? If everybody's on board, it'd be great if every state were doing this. So the results, you'll remember that previous diagram that had facts about science was a good 90% and a little bit of doing science. Now it's split up in a different way. So we still have our facts because we do need content. Right now these are called disciplinary core ideas. So that's the content, students know. But then there's this huge 1/3 block of students do. Okay, so this is scientific and engineering practices. So you'll notice engineering is called out. Right now it's called investigation and experimentation standards, were the old California standards. They decided to call the practices mostly because they wanted to highlight science as a practice, that it's not just certain skills that you learn that skill, you're done, you learn that skill, you're done. It's kind of all wrapped together. Just the semantics thing, that's why they chose that, and they specifically threw engineering in there. And then the last category, in order to create more explicit connections among the sciences, they created what are called cross-cutting concepts. And we're going to go a little bit into each of these so that you can have a greater feel for all of them. Although we won't have time for you to understand all of them at all grade levels. But afterwards, if you want to come up, there's some more examples of seeing progressions across grade levels for the concepts and for the practices. And then all the DCIs, so we'll talk about, there's a lot of acronyms, are in this big document. Okay, so this is actually a really good shift, or a lot of us are excited about it, because it involves much more doing and making explicit connections. So right now, to get you to just think a little bit, we're going to start with the science practices. So those are the funnest. I want you to think, maybe you are a teacher or educator in some way and you make activities and you have a classroom. Or maybe you've been in a science classroom. You could think back to when you were in 4th grade. And I want you to think of an activity, and just after you have some thinking time, turn to someone nearby, share a description of the activity, and I want you to focus on 2 things. What was the goal? What was the objective that the students, you or your students, were supposed to learn? And what skills or parts of that scientific process did students actually do? Okay, so it'll take about 5 minutes. Think it out for a little bit, and then when you have it in mind, make eyes at someone, start talking. This marvelous activity, and we don't have time for everyone to share or capture this because we're doing this in quick mode. But can I have some folks who feel comfortable very briefly describing the activity and especially listing those skills that you felt it was designed to teach you to do? How about just the skills?
Okay, in Diana's high school physics classroom, they dropped different
objects
yeah.
off of
that
the
were
bleacher.
Uh-huh.
Yeah, we have to measure the time it took to fall.
Okay.
And then from that activity, we learned about gravity.
Mm-hmm.
We learned that different masses, different objects with different masses fall at the same speed.
and that some things that are more or less aerodynamic, but like weighing.
There's a misconception that like things that are less massive don't fall as quickly.
Right.
But what kids don't realize is that usually things that we compare that are more massive and less massive, the ones that are less are more air resistant.
Yeah. Okay, so the content there was about gravity, air resistance, and mass.
Mm-hmm.
And the stuff that you did was measure. Anything else that you did that's like a verb? You measured.
You observe.
You observe some stuff. Okay, so measure, observe, maybe calculate, maybe just watch crash. Anybody else? Yeah.
I sometimes do a water analysis experiment. It takes about 3 class periods, and the big strand is chemical reactions. reactions.
Okay.
I do a very short reaction of chemical reactions, and they have to figure out which heavy metals might be in a water sample, and they have to observe and they have to design the experiment. I don't.
So they do a lot of things. They observe and they design the entire experiment.
Yeah. And so I don't tell them
Wonderful.
no procedure. They have to figure it out.
I love that. Yes. Do. Excellent. Okay. Any other skills that you did?
So we talked about a preschool class.
Yeah.
Where, sorry, maybe not quite as relevant.
Preschool's totally education. Yeah.
So parents observed that there were a couple of kids arguing about whether or not a plastic flower would grow if they planted it in dirt and watered it over time. And so they created a curriculum, like a mini curriculum around it, where they measured how tall the flower was over time and recorded it, and then did the same with the not plastic flower and compared them, and so they sort of got a lot of like discussion out of the kids about like what it means for something to be alive, and why would something what lets something grow, and what and why do some things not grow.
Yeah, so there was a lot of verbs there. There was having an argument / asking a question about something. There was actually doing an investigation. There was measuring or recording. Maybe a little bit of calculating, but probably with help from the adults. And then engaging in discussion, or what we would call argument from evidence, and making some kind of conclusion too. So I've got a lot. So when they have to boil down, they actually boiled it down to 8 practices, and I'm just going to show you them for brevity. And it's hard sometimes to figure out, okay, when me and my team had to look at these, we spent several hours actually looking through them, but they tried their best to get it into a small list that other skills can fall under. So asking questions is big, and this matches with constructing an explanation. You ask questions, you find information, you construct an explanation. A big one that students need more practice with is being able to develop and use models. They have to, as we mentioned, carry out their own investigation, know how to do that. They actually not only do this investigation, but know how to interpret it. That's another big, huge thing that is takes a lot of critical thinking. It's kind of, some of us find it kind of interesting that they separated this analyzing and interpreting data and using mathematics and computational thinking. This is going to help a little bit to make it mesh well with the Common Core math, but they did end up separating this altogether. Engaging in arguments and evidence is also huge. And then this is kind of a grab bag, just obtaining, evaluating, communicating information, because it's getting information and spitting it back out. It's all of that kind of put into one. Also, even like the verbs like observing, which we think of as being a part of a lot of science. You know, does it go here? Does it go in asking questions? It's some of those verbs actually. These aren't mutually exclusive. We've found when we've tried to group different actions into them. But overall, every action we thought of, we could kind of put in here. One thing that I did want to point out, so where you see the asterisk and the underline, they really wanted to bring engineering into these new standards. But engineering does have a different process than some of the other sciences. So if you're doing a lot of the more, you're doing basically life science or science physics, a lot of times you are asking a question about the natural world or what you observe. You're planning an investigation in order to be able to construct an explanation based on evidence that you've gathered. That's kind of the way it works. There's a lot of steps. It's not linear. It's not linear, but that's how it works. But with engineering, you're doing engineering to solve a problem. So you're often just defining the limits of that problem, figuring out the requirements for you and what you need, iterating, and figuring out the solution. So it actually is a different process, and so they wanted to call that out. So you'll see that these are together, but really asking question goes with this, and defining problems goes with this. And anywhere in the standards, if you're online, or if you end up looking for this document, if you see this little asterisk, it means engineering. It means this relates to engineering, so just let you know. Yeah?
Where would you put, like, trying to formulate a hypothesis?
Yeah, so it's, they don't, if you look at all their there's a lot of background information about all of these. I think, I probably didn't print this one up. If you're talking about a hypothesis, I guess it depends on what kind of hypothesis it is. Sometimes when you're in like preschool, your hypothesis is really just asking a question. It's not figuring out you're not really doing it to the investigation level. Sometimes a lot of us put that in with investigations when my team did it. And then you just have to, when you're figuring out, does your evidence support your hypothesis or does it refute your hypothesis, we put it in with this. So that one also kind of, I don't think it falls in one of them. They do also, like all of these, for the grade progression, I think I pulled out one, construction explanation. They make, not all grade levels have to do all of these at the same level, like at the same amount. But it is something that hopefully all of these can, as you get older, you can do and do better because you built off what was there before. So just one example, I'm not going to read all of this, but if we look under practice 6, I'll just do constructing explanations. Grades K through 2, so younger elementary, what they are supposed to be able to do. Make observations to construct an evidence-based account for natural phenomena. Use tools. Generate or compare solutions. And then if you move up to upper elementary, it's very similar, but a little bit of a step up. Construct an explanation of observed relationships. Use evidence to construct or support an explanation. Identify the evidence that supports particular points in your explanation. Generate, compare multiple solutions. Gets longer. When you get to 6 through 8, basically all of these, it sounds very similar, but longer and longer and more qualifiers. For high school, they just get really long. Construct and revise an explanation based on valid and reliable evidence obtained from a variety of sources, including students' own investigations, models, theories, peer review, and the assumption that theories and laws that describe the natural world operate today as they did in the past and will continue to do so in the future. So a high schooler just has to do it to a different level than a first grader does. But they all are building off the same practice that you have to do in science all the time. Make sense? Okay, we're going to move on to cross-cutting concepts. One of the other slices in this pie. And for this one, what they tried to do is create concepts that go across the different disciplines that will help students connect them. And could be something that educators could try to make explicit to just bring them to the forefront. So in order to give you an example of these, does anyone have, when they look at here, knowing what they study, a cross-cutting concept that they would like to learn a little bit more about and understand, have some concrete examples about? We won't have time to do all of them. Whoever picks, I'll do it. Yeah, go ahead.
Stability and change.
Stability and change, so the last one. And why did you pick that one?
Because I think about it in relationship to biology, but I'm curious to see how it applies to other sciences.
Okay, so stability and change, here's just example. So example of progression across the grades. So in the young grades, K to 2, students observe some things stay the same while other things change, and things may change slowly or rapidly. One example of second grade of a performance expectation we'll talk a little bit about, but what the students expected to know at the end of second grade for earth sciences. Compare multiple solutions designed to slow or prevent wind or water from changing the shape of a land. So that has to do with things changing slowly or quickly, staying the same or changing. That's what kindergarten. By upper elementary, they measure changes in terms of differences over time and observe that change may occur at different rates. Students learn some systems appear stable, but over long periods of time they will eventually change. Middle school, students explain stability and change in natural or design systems by examining changes over time, considering forces at different scales, including the atomic scale. Students learn changes in one part of a system might cause large changes in another part. Systems in dynamic equilibrium are stable due to a balance of feedback mechanisms, and stability might be disturbed by either sudden events or gradual changes. And one example of a performance expectation for middle school in life sciences: construct an argument supported by empirical evidence that changes to physical or biological components of an ecosystem affect populations. So that just happens to be a life sciences one. High school looks very similar to the middle school. I'm just going to read the performance expectation for you. So if this was a physics one, students are expected to refine the design of a chemical system by specifying a change in conditions that would produce increased amounts of products at equilibrium. So totally different things that they're doing, and different disciplines, but all related to staying the same, changing, and different scales of that. Cool? So it's much easier to understand all that's involved in each one of these if you see it all the grades. We don't have time for this. We could do a whole workshop on that, and we do. But one thing that I did want to point out for this one, what you notice, if you have to think, if you've already heard about the Common Core standards, which are ELA and math, the good news is that these cross-cutting concepts also kind of help reinforce some of the concepts in those as well. So when you're learning other disciplines, it's not a huge stretch. So for instance, if you're doing math, they don't call them math practices. Does anybody remember the name for the math skills? It's a very optimistic, I can't remember what it is, but basically those mathematical skills, finding patterns, noticing them is one of them, and understanding scale is another. So that's a great overlap. For English language arts, cause and effect, and being able to make and argue from evidence is big, and then structure and function in terms of English is a little different, but it's still a big part of that discipline. And then for social studies, systems and stability and change. Poor energy matter alone, but that's okay. Okay, so we're going to kind of buzz through this. So this was the old standards. I mentioned before, mile wide, inch deep, but the new disciplinary core ideas. So this is that third piece of the pie. They wanted a limited number of ideas so that students can go deeper and just understand those core foundations. So if you take of all what science is, we, even in the elementary standards right now, we have disciplines. We have physical sciences, we have life sciences, and earth and space sciences. That's actually how they do it now in California. And they're going to continue to do that in the new ones. But they threw in this new one, which is called Engineering, Technology, and Applications of Science. I can imagine they were fighting over what words to use for a long time for that one, because it's very long. But this is where they're putting in the engineering, basically. The engineering, the new content that goes along with that. Just so that if you ever are going to look at these documents and want to get used to acronyms, I'm going to acronym this up, okay? So physical science, life science, earth and space science, engineering, technology, and applications. They shorten it, okay? Physical, life, earth and space, engineering, technology, and applications of science, okay? So these are just the disciplines. You take science, all the content, all that meat is going to go in there somewhere, okay? If you break this up into key core ideas, they tried to minimize it so that it was manageable, and they came up with 13. 4 for physical science, 4 for life science, 3 for earth and space, and 2 for engineering. Okay, so these are what are known as the disciplinary core ideas that fall under one of these disciplines. And what these disciplinary core ideas should be, they have to have broad importance, either across a bunch of disciplines, or they're just such a key idea in their discipline. You know, the kids have to start with that. It has to be a tool to get to more complex things. Remember, it's this foundation, that's why it's a core. Ideally, it would relate to the interests and life experiences of the students. So ideally, it'd be relevant in some way. They can connect with it. And in that sense, it has to deal with society or what we care about. And like the other strands, or dimensions of the framework, be teachable and learnable on a progression, okay, over multiple grades. And the DCIs that they came up with is this chart. So this is just actually straight from the framework, if you've ever seen the framework. So if you're in physical sciences, one of the big chunks, one of the core ideas is matter, is interactions. Another one's energy. These are really the only like totally new ones. If you compare them to current standards, they're just grouped into larger buckets. Hopefully, if you look at your favorite science or the one you're doing now, these resonate with you as being important core principles. So, but these are huge buckets still, right? So they needed to divide these into a little bit more manageable chunks. And so what they did is they have component ideas in each one of these 13. We're not going to go through all those. But just so that you see them, when you see these letters and numbers everywhere, you'll see that. So for instance, Earth and Space Science 3 was Earth and Human Activity. Earth and Human Activity has 4 component ideas, which I probably can pull up really fast. But I don't. Probably can't fast enough. But those Earth and Human Activity, those ideas will probably, if you look through the content, one would be that humans, because of their interaction with the different Earth systems, contribute to climate change, and yada yada yada. And so it's a bigger bucket for you to talk about just how humans affect Earth. And then that's probably the last one, actually, the hardest one. And then the 3 previous are building up to that. So each one of these component ideas, it's all about content. So this is the kind of stuff the students know X. This is that discipline-specific ideas that they should get. But it's far less in terms of, it's not as wide as it used to be. It is more focused, but if you read them, and it's not hard reading, but they're impressive. Okay, so they're actually good. It's a good base. It's not getting weaker just because it's not as broad as it used to be. So together, you've learned these 3. So we've got cross-cutting concepts, the practices, and the that meaty facts. And these come together into what's called a student performance expectation. So this is what the new standard is. If you looked at the standards in current California, it says students know that molecules are formed with multiple atoms. That's just all it was written. It was just the content, just that core idea. Now, a performance expectation mixes all 3 of them, hence this little thread thing, and tells you what students are expected to do. So, to give you an example, a couple examples. So here's one that's written, okay? By the end of the year, this is 5th grade, by the end of 5th grade, students should know how to obtain and combine information about ways individual communities use science ideas to protect the Earth's resources and environment. So in this case, this is that practice. Remember, this was actually the last practice, obtain and combine information about ways that we do blah, 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 blah. So this is going to be in some of the, probably Earth Sciences Resources content area. And in this case, not that you guys probably care at all, but 5th grade, this is the Earth and Space Science 3 component idea, and this is their first performance expectation for that. Another one for middle school, students would be expected to evaluate competing design solutions for maintaining biodiversity and ecosystem services. That seems pretty intense, right? I mean, that's like, walk up to an 8th grader and be like, will you please evaluate the competing design solutions? But this was going to help prepare a better workforce. In this one, you see this little asterisk? Remember, that means engineering. So this has to do with competing design solutions. So if they've already studied engineering, they've had a chance to do it, they've had a chance to create possible solutions to increase ecosystem services in some hypothetical or real environment, the students at the end of the year should be able to do this because they've already done it. Okay? And one other one, high school. They always get longer. earth sciences, students are expected to analyze data and the results from global climate models, so real world, to make an evidence-based forecast of the current rate of global or regional climate change and associated future impacts to Earth systems. So it's a step up. Okay? So these performance expectations, ignore this picture here. We have a cake metaphor going on in the longer workshop. They combine the 3 dimensions into what the students is going to be assessed. Okay, that's their assessment. That's how they should be expected to perform that. But what they're not telling you how to get the students there. So they're not the lesson itself. You don't have to make one lesson that does this, or one lesson that does this, or one activity. These are, at the end of the year, the students should be able to do that. So it's not telling teachers exactly what they have to teach or how to teach it. Okay, so they want to really call that out because that's the next step actually. Either providing teachers, educators with the curriculum or letting them do their own thing. But the assessment, this is what students will be assessed on. And we definitely won't get into this very long, but if you look at this document, this is how they look, okay? This isn't even a crazy one. But all I want you to notice, a little pointer, here's where you see the performance expectation. So this one's for kindergarten, and it says kindergartners should be expected to use observations to describe patterns of what plants and animals need to survive. That's what kindergartners should be able to do. Here are the practices, the skills, and it tells you some details. So it has all this text because it tells you they should be able to analyze data. What does it look like? For kindergarten, it looks like using observations from what they see or from media to describe patterns in the real world. So it gives you that, like, what does this look like? Bit. The disciplinary core idea, this is straight from the framework, that body of text that they created before the standards. This one happens to be one in life sciences, about organization of matter and energy, and it gives you like a sentence that explaining what they need to know. They need to know that animals need food, that plants need light and water, that kind of stuff. That content, that's that meaty content, the facts. And then the cross-cutting concept for this one is patterns. Patterns in the natural and human design world can be observed and used as evidence. So seeing patterns in nature. Okay? So that's what these all look like. And then down here, which is actually really cool, they actually aligned it to the Common Core, English language arts and math, which when your teacher is great because you don't have to worry about teaching 3 subjects, you could teach them all at once. And then here's just a whole bunch of cross-alignment to other grade levels. So I just wanted you to see that so it doesn't look crazy. And I mentioned this earlier, but the really good thing about these standards and the good thing about the Common Core is that they're a lot of the skills that we really need students to have in today's world, and they overlap remarkably well, which is great, especially if you're an elementary school teacher. So if you're teaching elementary school, if you are teaching a student to read, write, and speak grounded in evidence, that standard is in your Common Core ELA, your Common Core Math, and your NGSS science. So a lot of them, if you're engaging an argument from evidence, it's not just science, it's also ELA. So if your school district is saying, we're not doing science, sorry, we're not doing science, we're doing ELA, you can do it through science. So this is just a powerful visualization of, especially when you're communicating to teachers, this is not that hard, you can do it. Let's just do it through science. You have to hit these anyways, all of these, even if you don't do science. So let's just throw some of these that are very specifically sciencey too. Cool? Okay. Just to let you know about where we are and where we're going to go. So Common Core was at ELA and Math, and they were another national standard system. In 2010 is when they released them and said, okay, states, who wants to adopt them? Okay. 2010, they did that. Didn't take long for California to adopt them, a couple months, but it took us then another 2 years-ish to make an implementation plan. Okay, how are we going to make this actually work? And then they started testing out assessments, figuring out if they worked. Then school districts started teaching to curriculum that became available. Then they, and it took them different years for the math and the English. Then they actually administered the test that said, okay, now the tests count. This is this year, or actually it's next year, but they're starting it this year. A lot of school districts are doing Common Core now because they know that the tests are coming. But so just so you can see, from 2010 to 2015 is when they were put out to states for adoption, and then the tests become real. So it's about 5 years, okay? So compare that to NGSS. Just this spring, this April, they were released, 2013. So if it were the same timeline, it would take until 2018, maybe 2017, for the assessments to be ready and teachers to have curriculum and be teaching, and by the end of that school year, the kids be assessed. It took a little bit longer just because of scheduling for us to adopt, but California said, you know what, we're just going to take them as is. We like them. We were part of the lead states anyways. And we also, just one thing so that you know, just a couple of weeks ago, the State Board of Education had another meeting, and what they were trying to decide was how to do middle school. Because the interesting thing about the way they did the standards here for middle school, similar to how they do high school. For high school, if you're taking high school now, you're taking biology, you're taking earth sciences, you're taking that discipline level. And when you looked at the standards, it wasn't that hard for you to find what you needed to teach. And for middle school, it was similar. You took either life sciences, it was called, or earth sciences, physical sciences. But the way they put them in the new standards, they didn't let you know which grade was supposed to tackle which subject. Does that make sense? So just as for middle school, you need to know that the sun is the center of the solar system or whatnot. It doesn't tell you what grade you're supposed to learn that. And they said, states, you decide. Do you want them to do how we've done it? A lot of the states, where you add a certain grade, you often are learning that material, or do you want to integrate all the sciences? So you're taking integrated science throughout. You're taking a whole bunch of 6th grade, but it's all the different disciplines. A whole bunch of 7th grade, but it's all a bunch of disciplines. California actually recommended the integrated progression, which means that you're doing integrated science 6th grade, integrated science 7th grade, integrated 8th grade. And a lot of school districts or teachers were not happy about that. So they actually, rather than mandating it, they just recommended it. So now every district has to decide what they're going to do. So that's going to take some time, and that's going to be big. Yeah?
Where do you think that resistance came from?
I think it came from mostly teachers not knowing. If I've always been a 6th grade earth science teacher, now I've got to really change it up. Maybe I don't have a degree in physics, and I'm supposed to be teaching physics. So I think a lot of it actually came from the teacher level, the state they wanted to make the decision, but they kind of backed off. That was literally like 2 weeks ago. You could read about it in the newspaper. So our local school district, San Francisco, they're still deciding, what are we going to do? Yeah.
That brings me to the next question.
Yeah.
It is going to be very hard to implement if teachers don't have pedagogical content knowledge along with subject matter knowledge. Is there going to be textbooks to step up? Because many teachers I know love textbooks. Will they change the textbooks so they can support the teachers better?
So they're changing all the textbooks. So the next step is to, I should probably don't even have it here. Next would be start on some assessments to see how they're going to do it, and start building curriculum. So right now, actually, the state is pulling together people to be on the committee for the curriculum unit. And Smarter Balance is going to be the not firm, but the organization that is going to start with the assessments to try to figure out how might this look, and let's just test it out, kind of do some soft runs, see if it's going to work in the school districts before it goes wide. Common Core is actually doing mostly computer-based assessments, and so I think they're probably going to work off of their model. But right now it's in the curriculum phase. So until we get to where teachers, right now for the next few years, teachers in California, assuming they are teaching science in their classroom, still have to teach to the old standards because there are still going to be the tests at the end of the year for those standards, but at the same time they need to start getting ready for these new ones, because when these new assessments come out, they're going to come out. So it is going to be a shift, but that's what they're doing in ELA and math right now. So hopefully it's just up to us to help make that a little bit smoother landing. Okay, so how can informal science education institutions play a role? I'm just going to go through some examples, and of course I'm a little bit over. So in a way, low-hanging fruit, being on advisory committees, which a lot of us are, or at least there's a representative. Obviously it's great if educators are also on those advisory committees because they're in the classroom, and that's what they are doing so far, which is fabulous. We can actually develop curriculum or align our resources to it. So for instance, we're at Berkeley, you guys know the Lawrence Hall of Science, for the FOSS kids, or FOSS Science maybe. So that is curriculum that involves stuff that a lot of local school districts adopted, and it gave teachers something to hit the standards that is in their classroom. If a district adopts it, it means it goes to the teachers. And that's one thing that we could do. We could develop new materials, full curriculums, or we could just align what we already have so that it fits their needs. And almost everyone's just starting to do that. We could prepare teachers, professional training. I'll talk to a few of those. Smarter Balance is going to be doing the testing. We might not develop the test itself for the kids, but I'm going to speak to one assessment tool for teacher practice. And I don't want to diminish the importance of using other institutions as that relevant, that real world application of what they're learning in the classroom. It's great that we're going to have kids doing science now, not just reading about it, but actually going to see it in different places and figuring out why does this matter to us, to life, those destinations. So one example I wanted to play up as much as I can about Berkeley. This is like also really low-hanging fruit. So UCMP already has this wonderful website called How Science Works about the nature of science. If you haven't been there, go to understandingscience.org. And so they had all this content, and it does fit with the next generation science standards because it's about understanding science as a process. And so what we did is we worked with them to just throw it up on iTunes real fast, all the resources, as a tool for educators, actually, middle school and high school teachers, to understand that process better and use it with their students. This isn't actually my favorite platform because you can launch it, but just like any app, you have no clue how people are using it. And Apple probably is not going to change that. Thank you. So we found through our survey of this, it's only been out for a couple months, but a lot of people who are using it are actually students for their own knowledge, which is fabulous. But it's probably not a great professional development tool because you can't really track it and it's all up to the individual. It's self-paced, which is great, but probably needs something a little bit more in depth. So we've learned that doing things with teachers is one of the best ways. So this summer we just started doing NGSS workshops with teachers. It wasn't hard to sell them out because some of the most passionate ones really wanted to get in on it. And we did hours and hours of just the intro to what these are. And our institution happens to be collaborating with San Francisco Unified School District the most because it's our local school district. But I feel like a lot of ISEs are actually going to help the district get over this hurdle of how do we prepare all the teachers for this new shift. And we're excited to do it because we like the new shift. You could also do it not face-to-face but online. So this is just one example. You guys all heard of MOOCs, massive online open courses. Okay. This is just Coursera. I've taken many of Coursera course. But this is one that the Exploratorium's doing. It's called Integrating Engineering into Your Science Classroom. It's not called out that it's NGSS, but that is 100% NGSS. So this has the potential to, teachers anywhere can take it and really help get them more familiar and comfortable with how are they going to do that? What the heck is engineering anyways? We had spoken earlier to some folks, so BASI, a part of BASI, which is here at LHS, is SREI, Science-Rich Educational Institutions. Lots of acronyms. It's basically a group of organizations in the Bay Area and the local school districts. And this one particular initiative is to get the ISEs together for our own PD and our own alignment of what we're doing. So, for instance, next week, there's a large meeting down at Monterey Bay where the 6 organizations, which is Lawrence Hall of Science, Chabot Space and Science Center, Cal Academy, UCSF, Monterey Bay, Floritorium, figure out them all. We're going to get together to figure out, okay, we're all kind of starting on the next generation science standards. Let's make sure we have a shared language about what we're doing and start having a shared plan, because if we really want to help the system, we really want to support formal education, let's do it together. So we're just having a big, huge, fun meeting to start doing that. And the focus on that also is to figure out what everyone has now for professional development. One example of an assessment tool for teachers that we're working on, sorry, there's a lot going on this slide. Our Teacher Institute on Science and Sustainability is a 2-year professional development program for 3rd through 5th grade teachers, and it involves a lot of PD with us and then coaching in the classroom. And so we're starting to get them to understand the standards right now, and we're working with Susan E. Schultz's group at Stanford, and SRI is helping us scale a little bit to develop tools that teachers can use to reflect on their own practice, on what their students should be expected to do and know, and what they're doing. It's basically a rubric of look-fors in the classroom that aligns with the science practices. So we saw that list of 8 science practices. The first one was asking questions or defining problems. Just if you wanted to teach your kids how to ask questions and you needed a rubric, I know you can't read this, but for 3rd grade, a student should be able to, I can't even read this, identify testable versus non-testable questions. And a teacher should be able to do this. And these are just rubrics for a coach to help an instructor. Are you really doing this? These are the practices. Let's see if we could get these 8 practices. So right now, we're working with our cohort of teachers that is currently in the program to test out these tools and see if they're having an effect. And if so, then they can help a lot more teachers. And then, last but not least, I emphasize that a lot of your local institutions or just places are places where the kids can connect to science or do science. And so that's definitely an opportunity that can help bring together the doing science, the cross-cutting concepts, and the core ideas in a way that's really relevant. So those are just a handful of ways that some of our local organizations are starting to play a role in this. So enough of my talking. I would love to hear questions, or if folks want to have discussions about anything particular about what they've heard or what really resonated with them. I open the floor. Yes?
I am curious to know if you know or you think that engineering will be mentioned by name in the classroom, because one of the problems, maybe not in this area specifically, because there are a lot of engineers, but students don't know what engineers do if they don't know one themselves.
Well, I think the word engineering will be, and because part of, just as science is these practices, even though they're not linear, these are the things we're going to be practicing when they're doing engineering activities or understanding the engineering content. I'll try to find some engineering content as we go through here. They will have to use that word. So I think that part of the reason why students have no clue what an engineer is now, because they've never had to learn it. So the word will be used, even though it's a big one. They just solve problems, right? I'll try to find some content for you. Don't be shy.
But there's a question over there.
Yeah.
Can you talk a little bit more about the global warming?
About why states.
Well,
It's in here.
I know, and I'm a little
Climate
bit
change.
surprised that it's in there as an anthropogenic
Yeah, it's definitely is.
item,
Yeah.
and that all the states or so many of the states are adopting it, and
Well, so not all the states have adopted it yet, but considering the so the lead states are, even if they haven't gotten around to actually making their vote. Sorry, this is fast. I'm really smart. But So you'll see there's, not that we want to get political in here, but you'll see there's some red states in there. The idea is that states can adopt them and adapt them if they want. Ideally, they wouldn't do it so much that they're scratching out whole portions, but they're allowed to. So California could have done that as well. California could say, we're going to adopt them, but we're going to actually change X, Y, and Z. Probably not add too much, but shift focus. So states can do that. It would be a detriment to the whole system working, making it entirely equitable, but they're allowed to.
Because so many of the textbooks are based on the Texas curriculum, right? So
Yeah.
I would wonder whether or not they would decide to adopt this, and whether or not they decide to scratch out global warming or evolution or whatever would end up changing.
So I still think that's going to be an issue in terms of who's writing the curriculum. How many people are going to step people? How many publishers or bodies are going to step up to write curriculum? The publishing industry is going to have some sway, right? And that's why Texas has a lot, because they happen to have the one that's the most above water. But I think that's kind of the next big task, is who's going to write it and how are we going to get it funded? Which can be up to, many states can come together and do the same thing, or they could all go separate ways. So we don't all have to have the same textbook. We could all have totally different textbooks. But those textbooks will need to be aligned with the content that the state officially adopts. So it's still going to be an issue. That's not solved yet.
And evolution's in there as well?
Yes. Oh, yeah.
Unquestionable.
It's a key component. Yeah. You wouldn't be able to really, for the life sciences ones, you can't really, sorry, you can't really take it out. Right here. So you wouldn't really be able to scratch those two. I mean, I guess you could, but yeah.
Well, I was an engineer at LBL for 30 years and hiring manager and stuff. And personally, I would have been worried if someone came out of a school system in today's thing and then ignored evolution, whatever. But if this truly is trying to teach them how to do science and think like an engineer, then I, as a hiring manager, would be less concerned about whether they ever talked about global warming. I want to know that they can do the practice, and if they choose some other topic besides global warming, or you could do evolution and never mention humans, and I would be okay. I worked at the Joint Genome Institute. All we dealt with was bacteria. And as long as they know how to do science and so on, if these political decisions need to be made, it becomes less important to me. But today, in the old standards, if people didn't do evolution or don't do climate change, I wonder whether they know how to do science at all. But if I'm confident as an employer that they're coming out with these doing skills, I'm okay with whatever limited set of things that they want to do.
That's a good point.
I liked the UCMP's Nature of Science map.
Mm-hmm.
I saw the core ideas in the next generation science standards, but is there also an emphasis on emphasizing that the nature of science is not linear?
Yes, actually, when you look at the performance expectation crazy chart here, right here it says connections to nature of science. Scientific knowledge is based on empirical evidence, yada yada. This is about that. It doesn't use the same, in the framework it doesn't have the exact same bubble diagram in understanding science, but it's to the same point, which is great. But I also love understanding science's bubble diagram if people want to use that. You should throw it everywhere. Yeah?
I have a question about all the subdividing of the disciplinary core ideas.
Yeah.
Is that to help the continuity between teaching grades or
Why it's broken up into
down
disciplines?
into like common categories rather than just specific topics?
Partly just to be able to organize content and know what are the foundations that I need the kids to learn. It's basically that organizing principle. If I know that these are the 4 things that fall under heredity, what are the 4 things that they really need to know? It's it's breaking it down to the core rather than the nitty-gritty. Because the nitty-gritty was getting, as long as they know that, if they can list 6 atoms of the periodic table, it just ended up being no, they don't need to know the 6 items. They need to know that this is how what the periodic table does. So it was bringing it back to a level that allowed it to stay a foundation that then the kids could build off of. One example, just because I found one, of content under the engineering strands, as written in the framework, which in this case was called Influence of Science, Engineering, and Technology on Society and the Natural World. What they should know, the content. New technologies can have deep impacts on society and the environment, including some that are not anticipated. Analysis of costs and benefits is a critical aspect of decisions about technology. So that ended up being a high school one. But in that case, it has to do with, even though they didn't use the word engineering in the content, it's bringing in the real world part. So not all of them are going to use the word engineering in it. That was one example. Anyways, yeah.
I was just wondering, when you were talking about with the middle school and that maybe the middle school would be completely integrated and so you wouldn't have life science or physical science, does that mean that possibly you wouldn't have testing every year, that you would just have your performance statewide test at the end of middle school? That there might be a few
So that's actually how it is in elementary school. You get tested 4th and 5th grade. Really 5th grade is when everyone's stressing out. So deciding when they're going to assess, right now they're doing 5th and 8th, so it'll probably be something similar. But it's our call as a state. And they were designed, but that's a great point. Because the progressions are pretty tight, if I'm a 4th grade teacher and I start, with what I'm supposed to teach, it's assuming that the 3rd grade teacher really did finish everything, which is similar to how it is now, but there are jumps. If I teach 4th grade, maybe they didn't learn that content. They learned it back in 1st grade, and so whatever, I'm going to have to reteach it again. And that's a strength of the new standards in that you don't have to, there's not these huge gaps where they have 3 years where they never learn about something. But it is pretty, when you start, you're assuming that the students did get what they should have learned last year. So it's not really a change, but the progressions are pretty tight.
We have time for one quick question. Otherwise, thank you very much.
Thank you. I hope you're excited about that.